Welcome to the High Voltage AI podcast. This deep dive is part of a week-long series featured in the High Voltage AI newsletter on Substack, which, as you know, is designed to educate electric utility engineers on overhead and underground construction types, exploring why we use them and, the characteristics of each. We're on Tuesday of our series, and today we're diving into the fascinating world of passive safety systems and factory manufacturing for small modular reactors. Yesterday, we looked at the small modular reactor engineering revolution and career opportunities.
Yeah, that was a good overview.
Today, we're going to unpack the technical innovations that are making these small modular reactors, manufacturable for the first time, really, in nuclear history.
And what's really fascinating here, I think, is how removing literally thousands of active components in traditional nuclear reactors fundamentally changes the whole manufacturing game. I mean, we're talking about a real paradigm shift.
A paradigm shift.
Yeah, one that allows for factory production, leveraging expertise from industries you might not immediately connect with nuclear, like shipbuilding. It's a complete reimagining of how nuclear plants are built. And it's actually already happening.
Okay, so let's set the scene a bit. Traditional nuclear plants. They've always been, let's face it, a manufacturing nightmare.
Oh, absolutely. A nightmare is a good word for it.
So what exactly made true factory production just economically impossible for them?
Well, if we connect this to the bigger picture, traditional designs rely so heavily on these incredibly complex active safety systems.
Yeah.
And these aren't just, a few extra pipes or valves.
No, it sounds like way more than that.
It's a massive network. Mechanical, electrical components. Think about emergency core cooling. You've got multiple pumps, huge heat exchangers, accumulator tanks, intricate control systems, all needing to work together perfectly.
Okay.
Then you've got containment systems, spray systems, air filtration, hydrogen recombiners, big fan coolers, every single one of them active. They need external power.
Right, they need power to work.
Exactly. And then the backup power itself. Massive diesel generators, complex electrical switchgear, fuel systems, battery banks, all absolutely vital for safety, but incredibly complex to build and integrate.
And the control systems, too, I imagine.
Oh, yeah. Thousands of sensors, actuators, control panels, communication networks, all needing meticulous calibration, integration on-site. So the core insight, really, is that every single active component and how they all connect, it just transforms each plant into a unique, custom, field-assembled project. It completely defies standardized production.
Wow. That sounds like a monumental task, just managing the sheer number of parts and, like you said, how they all interact.
It absolutely is. I mean, You're talking about component counts, easily over 50,000 major components, each one needing an individual testing integration.
50,000.
Major ones, yeah. And the biggest challenge, most of these safety systems have to be assembled and tested right there on site.
Not in a controlled factory setting.
No, not like building a car on an assembly line. Each plant ends up needing unique system configurations, unique interfaces. And then there's quality control, doing nuclear-grade welding and assembly, often in challenging outdoor construction environments.
Yeah, that must complicate everything. Schedules, precision.
Exactly. It leads to delays, cost overruns.
Yeah.
It's almost built into the process, unfortunately.
And to really grasp the scale of this challenge, I guess we just need to look at recent projects. Like Vogtle Units 3 and 4 in Georgia. What did their experience tell us?
Vogtle is, a prime example. The AP1000 design, which was actually meant to be a simplified advanced reactor. Even that still needed extensive active safety systems.
Simplified, but still complex.
Incredibly. Consider this. It required 4 emergency diesel generators, each one with 6,000-gallon fuel tanks, all the support systems. It also needed 4-component cooling water pumps, heat exchangers, piping networks, plus 8 safety injection pumps, accumulators, complex controls.
Just listing it sounds complicated.
And the control room alone, massive. 18,000 indication points, 3,000 control functions.
Wow!
This unbelievable complexity.
Yeah.
It drove the construction costs for Vogtle 3 and 4 to $35 billion.
$35 billion.
Yep. And stretched the timelines out to 7+ years. It just clearly illustrates why these active safety systems fundamentally prevent true factory manufacturing and make these projects so incredibly difficult and expensive.
Okay. Given that immense complexity you just laid out for traditional plants, it really begs the question, how do these small modular reactors, with their promise of factory production, how do they fundamentally sidestep those challenges? What's their secret weapon, their ingenious solution?
Yeah, it's a great question. And the answer is, Well, it's almost elegant in its simplicity. Small modular reactors achieve manufacturability by basically replacing those active systems with passive ones.
Passive systems, so operating differently.
Completely differently. They operate purely through fundamental physics principles. Think gravity, natural convection, pressure differentials.
Things that just happen naturally.
Exactly. They eliminate the need for mechanical components, for external power, or even for operator action for, extended periods. Imagine this. Instead of pumps for coolant flow, you use natural circulation.
Gravity does the work.
Gravity-driven flow. Needs no electricity, no moving parts. For decay heat removal, you use heat conduction and radiation. Gone are the mechanical heat exchangers.
Yep.
Containment cooling, just ambient air cooling. No fans, no complex power systems needed there either. And for reactor shutdown, control rods insert depth by gravity. Again, no complex mechanisms.
So it's a radical simplification then.
It really is,
Yeah.
moving from these complex, custom-built systems to elegant, physics-driven solutions that are inherently safer and crucially manufacturable.
Okay, this is where it gets really interesting for me. NuScale's 77-megawatt electric reactor module. You hear a lot about it. It seems like a prime example of how this passive safety enables that manufacturing simplicity, but also actually exceeds traditional safety performance. Can you walk us through how it works?
Yeah, NuScale is a great case study. The technical specifications really demonstrate the depth of this revolution. Let's look at their core passive safety systems. Their emergency core cooling system, the ECCS.
Mm-hmm.
It operates using two-phase natural circulation, which means, again, no pumps, no external power needed, yet it can keep the core cool for over 30 days without any makeup water.
30 days without adding water. How?
Well, the vaporized coolant exits through reactor vent valves, it condenses up in the containment structure, and then it just returns via gravity-driven recirculation. Simple physics. And the system capacity is huge, between 263 and 711 kilograms per second primary flow rates.
That sounds like a lot.
It's more than enough for all the heat removal needed. I mean, that capacity can remove heat at rates comparable to what you'd normally need multiple large pumps for. But here, it's purely natural physics. Zero external power required.
That's a serious amount of cooling without any pumps running. And for such a long time, too.
Precisely. And then there's their decay heat removal system, the DHRS, same principle.
Mm-hmm.
Operates by natural circulation. Heat goes through steam generators and condensers that are submerged in a big reactor pool.
A pool of water.
Yeah, a large pool surrounding the reactor vessel. It removes 100% of decay heat indefinitely, again, with no operator action needed. The steam generator tubes transfer heat to that pool, and the pool then just passively rejects the heat to the atmosphere.
So it just sits there and cools itself.
Essentially, yes.
Hmm.
And it maintains a minimum 10-foot liquid level above the reactor core indefinitely. That's a huge safety margin.
And the containment, is that different too?
Very different. It's a steel containment vessel, but it operates at sub-atmospheric pressure. It's designed to stay below 30% of its design pressure, even during accidents.
Hmm.
And a key innovation is their helical coil steam generators.
Helical coil.
Yeah, instead of the traditional U-tube design. This eliminates the possibility of large break, loss of coolant accidents, major pipe break scenarios. And crucially, that removes the need for those traditional containment spray systems, the air filtration, the hydrogen control systems.
Yeah.
All gone.
So the engineering is definitely simpler, elegant even. But what does this really mean for the manufacturing side? How does this simplicity translate into real production advantages for, say, an engineer working on this?
Right. That's the key question. This leads directly to really transformative manufacturing implications. Because of these passive systems, you completely eliminate emergency diesel generators.
Gone.
All safety-related pumps.
Gone.
Containment spray system.
Yeah.
Safety-related HVAC system.
Also gone.
Think about that. No complex power backups, no massive pump arrays, no intricate spray networks. It means 99% fewer active components to integrate and test. 99%.
It's a staggering number.
It is. And this level of simplification is what enables true factory quality control in a controlled environment. It significantly reduces the amount of tricky field work required on site, and it allows for the standardized production of identical modules, much more like an assembly line.
And the numbers really back this up, showing superior safety, don't they? It's not just simpler, it's actually safer.
Oh, absolutely. The safety metrics are phenomenal. Core damage frequency, a key measure, is less than 1 times 10 to the minus 7 per reactor year. Compare that to 1 times 10 to the minus 5, which is typical for large reactors.
So 100 times lower risk?
100 times lower, yeah.
Yeah.
And the large release frequency, even better. Less than 1 times 10 to the minus 8 per reactor year, compared to maybe 1 times 10 to the minus 6 typically.
Yeah.
That's a monumental leap in safety performance.
Just an incredible improvement.
And the operational side is equally impressive. No safety-related operator actions are needed for over 30 days. And 0 external power is needed for any safety functions. It makes them incredibly robust, incredibly resilient.
And you said earlier, this isn't just theory, it's happening now. We're seeing major industrial players stepping up. Who are some of these key partners? What are they actually producing already?
Exactly. This isn't just on paper. The shift to factory production is well underway. It's leveraging established, heavy industry expertise. Take Doosan Enerbility in South Korea.
Okay, Doosan.
They have a massive 2.5 million square meter facility in Changwon. Incredible track record. They've manufactured 34 reactor vessels, 124 steam generators globally for traditional plants. They're so committed they made a $104 million equity investment in NuScale.
A significant investment.
Definitely shows commitment. And they've already manufactured over 2,000 tons of upper reactor pressure vessel forgings for 6 NuScale modules. Right now, 12 NuScale modules are in various stages of production at their facility.
12 modules already in progress.
Yep, and all of this complies with the highest nuclear quality standards, ASME NQ AWA1 and 10 CFR 50 Appendix B. These are the benchmarks for nuclear quality assurance and regulatory compliance.
That's incredible scale, and like you said, an established track record. Were there any particular hurdles they had to overcome in adapting their traditional nuclear manufacturing for these small modular reactors?
You know, it's less about major hurdles and more about optimizing what they already do incredibly well. Their deep expertise in large-scale component manufacturing pressure vessels, steam generators for big plants that transfers directly. The nuance is shifting from making bespoke, one-off components to standardized, repeatable modules, which actually plays to their strengths and efficiency.
Makes sense. Any other examples?
BWXT Canada is another prime example.
Yeah.
They bring over 70 of experience manufacturing naval reactors for the Canadian government.
Naval reactors, wow. That's high-spec stuff.
Extremely high spec. They've invested $80 million expanding their facility in Cambridge, Ontario. That'll create over 200 new jobs by 2026. They're targeting the first components for the BWRX 300 reactor designed to be manufactured this year, 2024.
So soon.
Yeah, aiming to support Ontario's Darlington deployment by 2028. And what's really crucial here is they leverage military-grade quality control systems, some of the most stringent in the world. That brings an even higher level of precision to the table.
And what about other players like TerraPower? How are they approaching this manufacturing shift? Are they doing something different?
Yeah, TerraPower's Natrium reactor. It demonstrates slightly different strategies. They're using established industrial partnerships really effectively, working with General Electric for steam turbines, Bechtel for construction management, basically leveraging existing heavy industry capabilities and supply chains.
So less vertical integration, more partnership.
Exactly. And they're moving fast. Site preparation for their demonstration plant began in Kemmerer, Wyoming, just this June 2024. They're targeting commercial operation by 2030 with a really ambitious 24-month construction timeline.
24 months? That's incredibly fast for nuclear.
It is. It just shows how different developers are finding various paths to factory production through these strategic partnerships. It proves this isn't a one-size-fits-all approach, you know?
It's really fascinating how these small modular reactors are benefiting from all this established expertise. Where exactly are these critical manufacturing skills coming from? You mentioned shipbuilding and naval reactors.
Yeah, this is such a crucial point. The naval nuclear industry, especially, provides a huge pool of ready expertise. And we're also seeing advanced aerospace manufacturing techniques coming into play.
Okay, tell me more about the naval side first.
Well, think about Huntington Ingalls Industries, HII. They're the sole designer and builder of nuclear aircraft carriers in the U.S. Over 25,000 employees.
That's a massive operation.
Huge. And they possess proven skills in things like nuclear welding that complies with ASME Section IX, the absolute highest standard for nuclear components. They handle heavy component assembly, routinely dealing with multi-thousand-ton pieces. Their military-grade quality assurance and quality control systems far exceed typical commercial standards.
And they have the people.
They do. They even have established 4 to 8 year apprenticeship programs across 19 different nuclear trades. So there's this ready workforce with deep, relevant experience. We don't need to build an entirely new skill set from scratch.
That's a huge advantage. So we're not starting from zero with training. What about the aerospace industry? You mentioned transferable techniques there. How are they revolutionizing small modular reactor manufacturing?
Absolutely. Advanced aerospace manufacturing techniques offer some revolutionary improvements for component production. Take electron beam welding, for instance.
Electron beam welding.
Yeah, it's a technique proven in making aircraft, engines, spacecraft, high-precision stuff. It can achieve an 85% reduction in the time it takes to weld a pressure vessel compared to traditional TIG welding.
85% reduction. How?
Because you can do it in a single pass versus maybe over 100 passes for traditional methods.
Wow, single pass versus 100.
It's not just faster, it's a fundamental shift. It reduces bottlenecks in manufacturing, significantly cuts down project timelines, and produces superior quality welds with a smaller heat-affected zone.
Okay, that's impressive. What else from aerospace?
Well, non-destructive testing methods. Things like ultrasonic testing, using frequencies from 500 kilohertz up to 50 megahertz to analyze internal structures without damaging the component. And radiographic testing, using X-rays and gamma rays for volumetric inspection.
So seeing inside the material.
Exactly. These provide enhanced, often automated quality control, ensuring a level of precision and reliability that would be incredibly difficult, if not impossible, to achieve consistently out in the field.
What about the specific materials needed for these advanced reactors? Are they exotic? And once these components are built, how do you actually move these massive yet modular pieces?
Yeah, the materials are definitely specialized. They have to be for a planned 60-year plant lifetime. But the transport challenges, believe it or not, they've largely been solved by other heavy industries already.
Okay, so what kind of materials are we talking about?
For the primary reactor parts, you're looking at things like SA508 Class 3 and SA533 Grade B Class 1, steels for the pressure vessels. For steam generator tubing, it's often in-canal 690, specifically chosen for its superior resistance to corrosion under harsh conditions.
And they need special properties.
Oh yes, they need high strength, minimum 550 megapascal tensile strength, and really good toughness, like Charpy V-notch impact energy, greater than 100 joules, even at operating temperatures. It's not just about being strong, it's about maintaining these very specific high-performance properties reliably under extreme conditions for decades. That consistency is key for factory precision too.
Makes sense. And once these high-spec components are built, how do they get to the power plant site? Like you said, we're not talking small packages here.
You're absolutely right. They're not small. Let's use the NuScale example again. A complete power module weighs about 700 tons.
700 tons.
Yeah, but here's the clever part. It's designed to be shipped in 3 separate segments. That makes transport feasible.
Ah, okay. Breaking it down.
Exactly. They use a mix of transport modes. Rail, which can handle maybe 200 to up to 1,200 tons. Barge transport for coastal or river sites that offers practically unlimited weight capacity. And then specialized trucks, things like self-propelled modular transporters or SPMTs. These things have like 44 to 60 tons capacity per axle.
Incredible machinery.
It really is. And once on site, they use heavy lift equipment like gantry cranes, 800-ton capacity, and strand jack systems, which can handle 15 up to 750 tons for really precise positioning. This whole integrated logistics and assembly system, it allows for that highly efficient 1-year site assembly and commissioning timeline.
1 year versus, what was it for traditional?
5+ years, easily.
Yeah.
Sometimes much longer, as we saw with Vosel.
Right. Okay. This all sounds incredibly promising, very efficient, but ultimately it always comes down to cost, doesn't it? What do the manufacturing economics look like, and how do we scale this up for mass production?
Yeah, you hit the nail on the head.
Right.
Cost is critical. And this is where the long-term vision really comes into play. Now, early production costs are high. That's typical with any new technology. Initial R&D costs, lower volumes.
Sure, you have to amortize those initial investments.
Exactly. But the underlying economics are clear once the volumes increase. We're projecting, based on studies, a 40 to 60% reduction in capital costs compared to traditional large reactors.
40 to 60% lower upfront cost.
That's the target range.
Yeah.
And those construction timelines we just talked about, 1.5 years versus 5+, that's a huge cost saving in itself, just in financing and labor.
Definitely. And you mentioned a learning curve.
Yes. Crucially, there's that expected 15 to 20% cost reduction for every doubling of production volume. That's the classic manufacturing learning curve effect in action. It's fundamental to scaling any manufacturing process, whether it's cars or computer chips or now reactors.
So how many units do we need to build before these cost savings really start to materialize? And is that kind of demand actually realistic?
Good question. Break-even analyses They generally suggest somewhere in the range of 40 to 70 units are needed to get truly cost-effective factory production rolling, with the full benefits really kicking in at maybe 100-plus units produced annually.
Okay, 40 to 70 to break even, 100 plus for full benefits. Is the market there?
Well, the good news is the current global pipeline, just what's publicly announced or under serious consideration, is around 22 gigawatts. That translates to over 150 small modular reactor units. So yes, the potential future demand seems sufficient to achieve those necessary economies of scale.
So the demand signal is there.
It appears to be, yes. But of course, the current challenge remains those higher per unit costs for these first-of-a-kind or early production units and spreading those initial R&D expenses over a limited number of initial orders.
What about the actual factories? Are we seeing companies building the facilities needed for this kind of mass production? Is that commitment happening?
We absolutely are. Holtec International's facility in Camden, New Jersey is a great example. It's huge, 500,000 square feet, already capable of producing nearly 1,000 pieces of heavy equipment annually for the traditional energy sector.
Okay.
And they've announced plans for a massive $7.4 billion expansion specifically for small modular reactor production. They're targeting their first SMR 160 reactor to be operational by maybe 2028 or 2029.
So serious money being invested in capacity.
Very serious.
Yeah.
It demonstrates real industry commitment to scaling up production, building out this global manufacturing network with partners like Doosan and BWXT, and developing the robust nuclear-grade supply chain needed to support it all.
Okay, so bringing it all home now for our listener, especially if you're a manufacturing engineer listening to this, what's the bottom line here? What should they take away?
Right. The bottom line is this. Small modular reactor manufacturing represents this amazing convergence of passive safety innovation, basically simplifying the physics with proven, established industrial techniques. This simplification is what fundamentally enables the shift to controlled factory environments, making it a viable and, I think, really attractive new sector for manufacturing expertise.
So for engineers, what are the key advantages?
Okay, for manufacturing engineers, I'd say. First, technical simplification. Passive systems eliminate, like we said, 99% of those complex active components. That's what makes factory assembly possible in the first place.
Right.
Second, there's a proven manufacturing base. Naval, nuclear, aerospace, heavy industry. They already possess the necessary skills, the quality systems, the workforce. It's not starting from zero.
Huge advantage.
Third, production is a reality today. Components are being manufactured right now by companies like Doosan, like BWXT. This isn't just theoretical anymore.
It's happened.
Fourth, quality enhancement. Factory production means you get precision manufacturing, you can use automated processes, you have much better, more consistent quality control because you're in that controlled setting, not out in the field.
Makes sense.
Fifth, the economic pathway is clear. The foundation for cost-effective manufacturing is laid. It's just waiting for sufficient production volumes to really drive those costs down the learning curve.
And finally,
workforce transition is streamlined. Expertise from maritime, from aerospace, it transfers directly. And those established training programs, like the apprenticeships at HII, are already in place. It's truly a testament to engineering ingenuity, isn't it? To simplify something so inherently complex down to leveraging basic physics and existing industrial strength.
It really is. Okay, that's our deep dive for today. A fascinating look at how passive safety is unlocking factory production for small modular reactors. And remember, this is just Tuesday's installment in our High Voltage AI Newsletters week-long series.
That's right.
Tomorrow, we'll be exploring grid integration and industrial heat applications. We'll be looking at how these reactors can provide flexible grid services that go way beyond traditional baseload power. We'll examine their load-following capabilities and also their potential for industrial heat applications, which could really transform both the electricity market and industrial process heat markets.
Yeah, it ties together nicely. Passive safety provides that technical foundation for manufacturing them efficiently. And then grid integration and these industrial applications, well, they provide the market drivers, the demand that justifies building them at scale.
Exactly. So as you think about what we discussed today, we want to pose a question to you, our listener. What manufacturing experience do you have that you think could transfer to small modular reactor production? Are you seeing opportunities emerging in nuclear manufacturing, maybe at your company or in your region?
Yeah, we'd love to hear if you have experience with advanced manufacturing techniques, specific quality control systems, maybe from aerospace or heavy industry, that you think could apply here.
Absolutely. Share your thoughts. And if you'd like to leave feedback on today's discussion or have any questions, please feel free to reach out to our producer, Julius Guwe. That's Gwayy on LinkedIn.